Welcome to lesson chapter H7-4, Graphing the Cosine Function. Our objective today is to discover the relationship between the cosine and the coordinates on a unit circle and looking at the Pythagorean identity. Okay, so we won't actually even do much in terms of graphing the cosine function today. We'll get into that later in the week as we progress further into the lesson. All right, so let's go ahead and get started. First thing here, we've been talking about a model of a unit circle called the screamer, but we are going to start looking at what we call the unit circle. Okay, and this is just a very basic introduction to it. We'll get more detailed as we get deeper into it. But by the words unit circle, obviously we have a circle, and what's important to remember about that circle is that the radius is going to be 1 unit. So if you see we have our x and y axes on here, if we were looking at points that appear on this, we'd have a point over here at 1, 0, right? Our x coordinate for this point is 1, 0. At the top, we'd have the point 0, 1. Over on the left side, we'd be at the point -1, 0. And at the bottom, we would have the point 0, -1. All of these, like if you're looking at the x-axis, that is 1 radius there, and that is 1 unit long. This radius is 1 unit long. This radius is 1 unit long, and so is this. Now, any radius we draw on the circle would also be considered 1 unit long, right? Because it's not going to change the length of the radius. So if I drew a radius out here to the edge of the circle right here, this radius is 1 unit long. These are all 1 unit long. Now the point out here, right, would have some different coordinates, and that's kind of what we're going to be looking at here today. So problem 7-45. Find the coordinates of point P on the unit circle below. Is there more than one way to find point P? Be prepared to share strategies you have used. Well, here is our point P here, and this is a unit circle, so you'll see here that this radius length is 1 unit. And we know here that this angle inside of here is 34 degrees. Now, if we're trying to find the coordinates of P, we need to figure out, its x coordinate and its y coordinate. So as we look at this here, if I drop an altitude down here from our point P straight down to our x-axis, you'll see that we have a right triangle formed. This distance along the bottom here, right, is like our horizontal distance there. We'll call that x, okay, because P is x units, right? It's x units from the origin from left to right. And P is going to be y units up from the x-axis here. So we're going to be looking at how can we figure out what these two coordinates are given that we have a 34-degree angle in there. Well, if you've been paying attention to what we've been doing in class, we discovered recently here that we can find the height of any triangle here by using the sine function. So we could look at this here as saying, if I have 34 degrees, and I'm talking about y is my opposite side, and then I know that my hypotenuse is 1. So I could say here that the sine of 34 degrees should equal y over 1, which simplifies to just y. So if I can calculate what the sine of 34 degrees is, that will tell me what my y coordinate is going to be. So let's use a calculator to get that. So first thing here, my calculator, need to make sure it's in degree mode because we're talking about degrees right now. I'm going to go ahead and do the sine of 34 degrees. Hit enter there. And it looks like it's 0.55919. So we're going to just go ahead and round it for now. We'll say it's about 0.56. So our sine value that we got was about 0.56. Okay, well that means here that this distance on the side is about 0.56. So our point P is going to have a y-coordinate of 0.56. Now we need to find our x-coordinate. And there are all different ways here that you could do this. I know that some people will look at it and say, hey, well, the adjacent side down here is x, and we still have our hypotenuse is 1, so we can continue to use this angle here, except instead of using the sine function, we could use the cosine function, right? We could say the cosine of 34 degrees is going to equal x over 1. And now we can go ahead and calculate that to figure out what our x value would be. Let's just do it on the calculator. We said that the cosine of 34 degrees is going to equal about 0.8290. So we'll round that to 0.83. So 0.83 would be our x value. That means that we're traveling to the right 0.83 from the origin. That means our x-coordinate is 0.83. So this should be the values of our coordinates of point P. Now, is that the only way to do it? No, there are other possibilities that could happen here. I've had some students who, once they figured out that this was the y value, they went ahead here and they looked at this just as a right triangle, right? And they said that they were going to do the Pythagorean theorem to help them figure out what x was, right? You could do that. You could say x squared plus 0.56 squared is equal to 1 squared, and you could go through and solve that. You should get something similar to 0.83. However, we've rounded, so we may have altered it a little bit. If any of you try that, that's a good thing to think about. And we're going to talk about this. We're going to talk about this here a little bit more in just a moment. Now it says generalize what you found in problem 7-45 to write the coordinates of point Q on the unit circle below. Well, remember on the last problem here, right, when we drew this down here and we drew that right angle, we figured out that for our x's and y's, we could find them by doing different trig functions with our angle. So this angle here, we said that if we did the cosine of whatever the angle was, it gave us our x-coordinate. And if we did the sine of theta, it would give us our y-coordinate. So if we were going to generalize there, we can always find the x-coordinates of our points by taking the cosine of the given angle, and we can always find the y-coordinates by doing the sine of the given angle. So in other words, what can a sine value tell you about a point on a unit circle? The sine value can give you the y-coordinate or its vertical distance from 0. And what about the cosine value? Well, the cosine value can give us the x-coordinate. Or the horizontal distance from 0. Okay, those are important to remember there. We need to remember that our sine value is our y-coordinate, or the vertical distance, and our cosine value is the x-coordinate, which we refer to as the horizontal distance there. All right, so let's go to 748. If you know the sine of an angle in a unit circle, can you find its cosine? How? Work and find a strategy and be prepared to share. So with this one here, if we were thinking about, let's say, for instance, we knew here that we had a right triangle here, and we were trying to find, this is just like part of the circle here, right? We're going through and putting it on there. Let's say here our sine value for this angle that we've got was, I don't know, let's say 1/3, right? So if it was 1/3 there, they're asking us, hey, how could we figure out what x is going to be on the unit circle here? Okay, so if I have 1/3 and 1 there, we could take it there and we could look at either finding the angle, right? One strategy is we could use the inverse sine to find the angle, and then take the cosine of the angle. Right? So, or a second method here we could probably use here is what we started talking about in that first problem here, is we could probably just use our Pythagorean theorem. Right? I could say here, in this case here, for the Pythagorean theorem, I could say x squared plus 1/3 squared should equal 1 squared, and we could go through and we could solve that to figure out what it's going to be. For that first one there, right, we could say that the sine of theta would have equaled 1/3 over 1, which is would be 1/3, and then we could have found the angle by doing our theta equals the inverse sine of 1/3, and after we got that value there, we could then take, the cosine of whatever that value ended up being there to get our cosine value. So those are the two methods here that we probably could use that we already know how to do. Let's take a look here at what this is building towards. So 7-49, an angle theta on the unit circle has a cosine of 3/4. Okay, it says find the exact coordinates of point Q by using the Pythagorean theorem. Okay, so this is why we didn't solve the last one, because I knew we were going to be solving one here. So as we look at this here, we've got our point Q on our circle. I'm going to go ahead and just draw in that right triangle, or that part of our bow tie there. And if we look at that there, we can say here that we've got our x coordinate already, right? We already said that this, if it has a cosine value, that's going to be 3/4. 3/4 is our x coordinate there. We need to figure out what the y coordinate is going to be. Well, if this distance is 3/4 and the hypotenuse is 1, we can find our y value using that Pythagorean theorem like they want us to. Let's do it here. So for part A here, we're going to do 3/4 squared plus y squared is going to equal 1 squared. 3/4 squared is 9/16 plus y squared is going to equal, well, 1 squared is 1, but I'm going to take it and turn it into 16/16 just because I know that I'm going to be subtracting this 9/16 from each side. And after we do that there, we've got y squared is equal to 7/16. Now, when we take the square root of each side, we're going to end up with the absolute value of y is going to equal the square root of 7 over the square root of 16, which should give us the square root of 7 over 4. So y could equal positive or negative square root of 7 over 4. Okay, because right now we know that this point could be up the square root of 7 over 4. But remember, there's also a second point on our circle here that would have a cosine of 3/4. There's also a point down here that has the same x coordinate, right? This one would be 3/4 comma negative square root of 7 over 4. So just something that we have to start thinking about here. We can't just say the square root of something squared is just a positive right now. We actually have to look at the positive or negative versions. Okay, so we found our coordinate there. We said that it could be the point 3/4, comma, it could have positive or negative radical 7/4. Says what is the value of the sine? Well, it's either one of those, the positive or negative square root of 7/4. And then it says the Pythagorean theorem becomes the Pythagorean identity when we input the trig expressions, the sine and the cosine expressions into it. So what does that mean? Okay, so if we think about this here, right now all we did here, I'm going to draw this triangle just a little bit bigger. All right, we had our theta. What we ended up doing here is we had this 1 out here. To find our point up here, our x coordinate and our y coordinate, right? We could find either one of those by squaring them. Okay, so this is the same thing as saying with a right triangle, okay, we could say, and I'm going to actually write it on the other side over here where there's a little bit more room, but we know because it's a right triangle that x squared plus y squared equals 1. Right? Now, we also said here that we can find that x coordinate by doing the cosine of theta, and we can find the y coordinate by doing the sine of theta. So these could be substituted in here. So if we did that, we could say this is the cosine of theta squared plus the sine of theta squared equals 1 squared, or, which would still be just 1. So what you're seeing now is this Pythagorean identity that it's talking about is just a different form of the Pythagorean theorem. Okay, it's when we don't have the x's and the y's, and then we now have the trig functions. Now, you're not going to see it written that way a whole lot, okay? This way here is really good for the calculator, right? If you're going to type it into the calculator, you're going to have to write it like that. What you'll actually see written by most mathematicians is they take these squared terms here and they don't actually put them out there behind theta. The way it will actually be written most of the time when you see it is going to be the cosine squared theta plus the sine squared theta equals 1. This is the way you will see it most of the time. Okay, it means the same thing, right? Remember, that's the calculator one up there. This is just the way we typically write it here. This is, the formal way of writing it. So that's the formal version, we'll call that there. Cosine squared theta plus sine squared theta equals 1. It means the same thing as what we wrote up above in the box there. Okay, but you need to start to familiarize yourself with that. We'll deal with it a lot more later in the year, and you will use it a lot more as you get into pre-calculus and calculus in future years. All right, let's finish this out. The last problem in this lesson said, remember the scary Ferris wheel, the Screamer? LaRasha does. She was riding the Screamer sitting 27 horizontal feet away from the central support pole when the ride stopped. What was her seat's angle of rotation? Is there more than one possibility? Justify your answer using as many representations as you can. So, number one thing I would say to you here is it's going to help you to draw a picture. So I'm going to do my best to draw a circle on here. Hey, that's not too bad. We'll take it. And I put my x and my y axes. Now, big part of this, she's sitting 27 horizontal feet away. So they're giving us the x coordinates of where she could have been at. So if we think about it here, if we measured out 27 feet out to the right here, right, we'll say that's 27 feet. She could be up here. She could be down here, right? Both of these have the point 27 comma something. But it also, she could be back on this left side. She could be 27 feet back this way as well. That would be 27 feet from the central support pole as well. So what we're going to look at here is the fact that there are several angles that she could be at. She could be at 4 different places on the Screamer there. So 4 different locations. Her angle could have opened up here to there. It could have opened up over to here, right? So we could have gone from here to here. We could have gone from here all the way to here. Or she could have gone all the way around to down here, or almost all the way around. So what we're going to look at here is we've got 4 corresponding angles here that we can kind of use to help us figure out where she's at. So now, one thing to remember with these kinds of problems here is that the radius of our screamer was 100 feet. So what we need to figure out here, and if I'll draw this first triangle just a little bit larger so you can follow along. All right, we've got this is that triangle there from the first quadrant. We're trying to figure out what this angle of rotation is. So we have this is 100 feet. We know this is 27 feet. So if we want to figure out what theta is, we're going to use the adjacent side and the hypotenuse. So the cosine of theta should equal 27 over 100. And now we can find theta by doing the inverse cosine. So what that's going to get us here is, and let's go ahead here and just do it on the calculator. We'll do second inverse of cosine of 27 divided by 100. And remember, we're in degree mode on our calculator. So it says, it looks like it's about 74.34 degrees. Whoops. There we go. So this is going to be about 74.34 degrees is what she would have been rotated in the first quadrant, right? So here, 74.34 degrees. So as we look, though, at other angles, let's say she's gone from the start all the way around to here. Okay, so remember, when we're dealing with, our angles in our unit circle here, we've already talked about our reference angles. So if we think about the angles we've got in our bow tie, right, this was 74.34. And if we draw in that bow tie, right, we know that that 74.34 could be here. The angle that this one makes with the x-axis is 74.34, and same thing in quadrant 2. This one's 74.34. So that first one here, we already said was 74.34. This one, as we go to here, we are 74.34 degrees away from the x-axis when we get up there. So on the left side, we've already talked about, we can do 180 minus 74.34. And that should give us, I believe, 105.66 degrees. I hope my math is right. I don't want to redo this video. You know what? Let's just go ahead and double check that. 180 minus 74.34. 180 minus 74.34. Enter. 105.66. Go, Mr. Boyd. Here we go. So that's the angle that went to here. If LaRasha went all the way around and she was stuck down here, now she's 74.34 degrees past 180. So we're going to do 180 plus 74.34. So when we add those, that looks like it's going to be 254.34. You can double check it on the calculator and you can let me know if I'm wrong. I'm pretty sure I'm right on that one. And then remember, for that last angle, she could have gone all the way around here until she got to this point, which is going to be 74.34 degrees away from 360. So we're going to go backwards, 360 minus 74.34. And we'll use the calculator for that last one so I don't screw it up. 360 minus 74.34. Enter. We get 285.66. So 285.66 degrees. So what was her possible angles of rotation there, right? There is more than one possibility. LaRasha could have been at 74.34 degrees. She could have been at 105.66 degrees, 254.34 degrees, or 285.66 degrees there. These are the possible angles of rotation that LaRasha could have been stuck at there. If you have questions about these kinds of problems, you need to make sure you're asking there. Otherwise, hopefully this helped you if you weren't in class. Thanks for watching.